Your hand. Anyone that knows the book? 1, 2. Anyone that does not know the book, please raise your hand. Oh my God. Okay, so if you know the book, you are going to enjoy the talk. If you don't know the book, I hope that you also will join the talk. My name is Shai Rubin. The book is about compilers, and we are going to talk about compilers, specifically about some infrastructure under the compiler, and in the context of Python. As I said, my name is Shai Rubin. I am a software engineer at OnBackup. And if you want to know more about OnBackup, then you are welcome to our booth outside with a roulette, and you can have some prizes. I'm not going to talk about what I do at work, but actually what I'm not doing out of my work. And I'm going to talk about the fun with AST libraries that I am developing. And I hope that we are going to have fun. So what are we going to do today? First of all, we are going to talk about abstract syntax trees. And especially in the context of Python. Then we will see some limitations and challenges in the AST library of Python, and I will present the Fun with AST library in which we are trying to address, or I'm trying to address those challenges. Just before we begin, don't worry. 12:30, you will be at lunch. This is a Python program. 1 plus 2 equals 1 plus 2. When a compiler or interpreter tries to take this program and put it on a machine, on a CPU, they need to translate the text to machine language. And the way to do that, one of the things that compilers are doing during this compilation process is to construct abstract syntax trees from the code. If you can see, this is a tree. The first module, the first node is a module node. Any file in Python will start with a module node at the head of the tree, at the root of the tree. And then you have the assign statement, which is also matched to the assign statement in the program, right? There is an assign statement there. At the left side of the abstract syntax tree, you see the name node, which is 1 plus 2, and the store operation, which is essentially a variable in Python that says that this is a variable, and we are going to store into this variable. And on the right side of the assign statement, you see the binary operation, the add, and the two constants, 1 and 2. So it is easy to take this. It is easy to understand that the source codes there actually translate to this kind of a formal representation that is called, in many compilers, abstract syntax tree. Okay, so why they are important? Why they are important in compilers? They are used for many different usages. The first one that we were speaking now is about the parsing and validation. If you cannot parse a program into an abstract syntax tree, then it is invalid program. The second usage is parsing, is code generation. You can actually see that it is relatively easy to take the abstract syntax tree and translate it into some machine code, right? The store node is to store something in memory. The binary operation is an add operation. It is easy to traverse the tree and to generate the code. Transformation and optimization. Many compilers, even the most dumbest one, will take, for example, the binary operation add, figure out that there are two constants here, 1 and 2, and actually will not generate the add. They will transform the program into 1 plus 2 equals 3 and remove the add from the machine. So the program will run faster. Analysis and program understanding and programming tool, everything that we are using, almost are using the abstract syntax trees, for example, linters, all static analysis that we do on a program. If you are using a modern IDE and you are doing refactoring, you can mark a piece of code and then move it to another module or to another method, for example, refactor into a method, are using abstract syntax trees in order to ensure that the correct transformation. Okay, so this is a little bit of introduction to abstract syntax trees and their use in compilers. Now let's see how Python actually is doing that. On the left side, you can see a simple Python program, the if statement with a one statement. It's a one statement in Python. And on the right side, you can see the abstract syntax tree in Python. So there is an AST module in Python that enables us, the programmers, to actually take the source code and generate an equivalent abstract syntax tree. I don't know if it is the actual abstract syntax tree that is used in Python, which is implemented in C, as Edith told us previously, but it is probably very close. And this is the AST model. If you look at the if statement, there are three subtrees to the if statement. The first is test, body, and or else. These are fields in Python of the if node. It's a data structure. The test actually is a subtree of a compare abstract syntax tree, which is, you can see a quality of A to the value 1. Then we have the body abstract syntax tree, which essentially will hold the list of instruction under the true part of the if. In this case, it's only B equals 2, or assign 2 to B. And the or else is a list of instructions and statements that will come under the else part of the if. Okay, so this is cool. This is nice. One thing to note, though, if you are using Python, then there is no else if. Where is the else if? Right? There is else if in Python, but we don't see it here. Well, the implementers of Python decided that they will implement else if by or else field and immediately followed with another if statement or an if node. So this is an insight that we get when we learn about those ASTs. Okay, so this is cool. And let's see, and what is even more cool is that actually you can take an abstract syntax tree in Python, use the AST module in order to have the source code, the original source code on the left. Well, almost the original source code, right? Because something is missing there. It's the same program, but for example, the comments are left out. So the transformation back and forth is not complete. And this is a program I found on the internet. It should be a Python program. It is running in Python. All the Pythonist people here will excuse me, but this is from Geeks of Geeks, which a program that actually calculates Fibonacci series. And you can see that a Java person actually wrote it, which is fine. Okay, this is the way they wrote it, and they wrote it for humans. The persons that wrote this program wrote it for humans, right? There are comments at the beginning, there are white spaces, the variables are not always spaced equally, and it is relatively easy to learn maybe Python. Well, if you parse it into an abstract syntax tree and back, you get this program. You get this source code, much more condensed. Some characters are actually missing, for example, the brackets, which are unnecessary in Python. Of course, all the comments, all the white spaces. This makes sense because the compiler does not need those. But for us, for humans, it will be much more difficult to read. So when I saw that, I said, okay, can we make sure that actually can we write code that actually preserves the source code even when we are actually building it from an abstract syntax tree? Okay, so we have one challenge to preserve the source code. We want to preserve the source code when we translate from abstract syntax tree back to source code. And then when you look at this, you say, but until now, we are used to write source code and to translate it into abstract syntax trees. What will happen if we take the abstract syntax tree, modify it, and get another program? And for that, for example, I give an example here. If you are taking the 4 and 5 and change the values there in 4 and 5 and translate back into source code, you will get a new program. It will be great if you can even change the comments, right? So now we have another way to write programs, if we want, using abstract syntax trees and get a new program from the original one. So this is a second challenge I want to solve. So where are we? We discussed a little bit the abstract syntax trees and Python. I presented two challenges or limitations of the AST model of Python, and now I'm going to introduce the fun with AST library. If you want to address those challenges that I raise, you will need to learn the AST model of Python. And if you remember, if you want to modify anything in the abstract syntax tree, you need to be very specific. You need to know exactly where you need to change and what you need to do. And this is a lot of work of the nitty-gritty details of the AST model. The fun with AST library actually suggests a different interface to modify programs. Instead of actually working directly on the abstract syntax trees, we will use source code, a new source code, in order to modify the original program. And then everything becomes much more easier. For example, if you want to add an instruction to an if statement, the if statement on the left, and we want to add a node, the print, this is fun, in the if body. If you will try to do that with the AST model, yes, you can. It will require a lot of work, a lot of understanding of the AST model of Python. However, with the fun with AST library, this is all the code you need. And essentially, it's very, very easy to read. The first 3 lines just define the variables, the original if source and the source to add, right? And then you are using the fun with AST library to actually create the original node, the if node, create the new node you want to add, and with one line that is marked with red here, you can add the node. And you will get the source code at the right. So instead of writing dozens of lines of code specifically for this case, you can actually write these lines of codes. Let's look at another example. The if invert example. If invert is a very common refactoring in which we invert the if and else, typically for performance issues. This is not a legal if invert, okay, because I don't invert the test of if, only the body and the else, right? The red goes to the else, and the blue goes to the if part. Okay, if you want to do that using the library, this is all the code you need to write. The first 3 lines are some initialization of the original if source and what you want, and then these 2 lines here above the red will take the original body source, the original L source, and then the red line actually do a replace body. It takes the original body source and put it at the place of the else body. And the blue line takes the original else source and put it in the if body. And with 1 line, 3, 4, or 2, 3 lines, you get the code at the right. Okay. Last thing that we need to do is to preserve the original source code. So this is more difficult to do, and I'm not getting into the detail now, but essentially in order to do that, what you need to do, or what I did, is I added a new object called matcher to every piece, every node in the abstract syntax tree library of Python. And this matcher is responsible to ensure that the source code that you got in order to parse the tree into parse the source code into an abstract syntax tree actually get the original source code. What are the challenges here? Here is our program from the beginning, and you can see that you can write it in many different ways, right? You can add the comment beginning at the end. You can even write it in this way: 1 plus 2 equals 3 equals 1 plus 2 and all the parentheses. All of them are the same program. It says the same semantic. Assign 1 plus 2 into the 1 plus 2 variable. In order to make sure that we can account for all these transformations, the Fun with AST library actually is based on the notion of placeholder. For every node, it has a list of placeholders that actually represent the structure of the node. For example, an assign node has 3 placeholders. The first placeholder is a targets, and essentially parse the target part of the assign. The second one is the assign symbol there. The second one is the value, which essentially parses the value. And typically at every statement, you can add the text placeholder for a comment at the end. And the library has a matcher, which is a default matcher, which takes this description and can actually ensure that, or almost ensure at this point of the development, that you actually get the original source code. Okay, I promise you will get to lunch, right? I keep my word. The library is available. Pip install Fun with AST, you can get it. The repository is open for the library, and also the test repository is open to contribution. Everything that I described is work in progress. The examples are real. These are actually works, and if you want to contribute to this library, please feel welcome to do that. Thank you very much. I'm open to questions at the end.